Greetings! Today we are going to be going over the basics of inverse trigonometric functions. I should warn you, if you have not learned about trig functions, or their graphs, or the unit circle and how they apply, this is not the video for you. So go find those other videos and learn about them, and perhaps come back. So we're going to be talking about inverse trig functions based on these trig functions. Actually, we'll be looking at only the top three, sine, cosine, and tangent. The first question I will ask and then answer are, what are inverse trig functions? Then I shall answer the question, are they functions? I shall answer it twice, because the first answer is no, and the second answer is sort of. Then we're going to talk about actually using the trig functions specifically in a context, which is important for reasons that will become apparent when I answer question number 2. So let's get into it. Let's begin. What are inverse trig functions? So trig functions themselves were built along the premise that if you know the angle for one of the acute angles in a right triangle, and you take that, what you need is a function that will take that angle and tell you the correct ratio of certain sides of the triangle. So for sine, you're going to stick in an angle into the function sine, and the answer to the function is going to give you the correct ratio of the opposite side of the triangle divided by the hypotenuse, which is information you should know. Now, the whole point behind the inverse trig functions is that in life, more often, we know the lengths of two sides of our triangles, and we're trying to find the angle. So this function, sine, is not actually useful in this case. What we need is the opposite function, where we stick in the ratio, opposite divided by hypotenuse, because those are the numbers we have, and it tells us the angle. And that's what inverse trig functions are for. If we know the correct ratio, it finds us the angle. And it's called inverse sine. You'll see it written sometimes with a little -1 superscript. You will also see it written sometimes as arc sine or arc cosine. They each have one arctangent. Moving on then, question number 2, are they functions? The short answer is no. If you take sine, pictured on the left, and you take the inverse of it, it rotates it around the line y equals x, which hopefully you've seen before, and produces this, which is not a function. It fails the vertical line test. For each x that you can enter into this function, there are an infinite number of possible answers. This is not a function. So the short answer is no. If you just take the inverse of sine, you do not get a function. This is a problem for us, especially in terms of computers and calculators. And generally in math, for functions, we prefer one answer to any question, please. That way we can mark students wrong. The longer answer is we can actually create an inverse function for sine, but we have to take sine and we have to cut so we get just one piece of it. And this is how we cut it. We needed to get all the possible answers so that we could, use them as all the possible questions for our inverse sine. And we chose the one in the middle. So we took the piece that was just from -π/2 to π/2. It gives us our entire range, -1 to 1, but we only get this one slice of it, so that when we turn it into its inverse, it's a function. Now it is 1 to 1, so its inverse is also a function. And we did this for all three of them just because we like functions. So this has both good and bad consequences. So, we can make it a function. We have the technology. As far as what this means for us, arcsine and arctangent have the same, well, pretty much the same range. They're going to give you angles between -90 and +90, or between -π/2 and π/2. For arctangent, it's a bit iffy because actually at -π/2, arctangent is undefined. So that's why it's got the parentheses. The actual endpoints you can't use. But you should recognize them in context. When you're dealing with something that has no thickness, only a length, then you should recognize you've got a problem with your triangle anyway. Now cosine, because of the shape of the graph of cosine, which I don't want to go into during this video, but if you take a look at it and think about trying to cut it off around 0, in order to get the full domain there, -1 to 1, we couldn't use the same angles as we did for sine. So our cosine actually gives you angles between 0 and 180, or between 0 and pi. So it's got a different output range than the other two. If you think about the unit circle, what this means is the arcsine and arctangent will only give you angles on the right-hand side because they are positive and negative in the first and fourth quadrants, whereas arc cosine will give you an angle on the top half of the circle, that is in the first and second quadrants, because those are the quadrants where x is positive and negative closest to 0. I suppose without going negative. So we get the full range of possible inputs by going 0 to pi instead of going negative pi over 2 to pi over 2. Otherwise, it'd all be positive ratios and things would be bad. So these have different output ranges and domains, but they all serve this same basic function. Now, these always output angles inside their, well, ranges. That should really say ranges. I'm not going to start over, though. That says ranges. I guarantee it. So these never return angles outside their ranges, which was the domains of the original functions. So what that means is you'll never get an obtuse angle from arcsine. It'll never give you an angle bigger than 90 degrees, which is a problem occasionally when you're looking for an angle that's bigger than 90 degrees. When you're dealing with right triangles, no problem at all. It gives you an acute angle. You needed an acute angle anyway. You're good to go. But for other triangles and applied contexts, it's a problem, which is why question number 3, or part number 3 of this lesson, is using inverse trig functions in context. So I have here proposed a question you might find. Find the angle that corresponds with the point -2, -3.46, which is something you should have seen before when you studied tangent and the unit circle. If you think about it, this point is in the third quadrant. It's in the bottom left. So when we're looking for this angle, we have learned that tangent, we can find its ratio as y over x. So if we take our y value, -3.46, and divide it by our x value, -2, we get 1.73. We want to find the angle, so we use the inverse tangent of 1.73. The inverse tangent of our ratio gives us our angle, 1.05, which, since you guys probably don't think in radians, is about 60 degrees. Looking at the actual picture, where we're supposed to find the angle that corresponds with this point, we actually draw the terminal side of our angle, and we note there is no way this is 60 degrees, because we're supposed to measure our angles from the positive x-axis. 60 degrees is this angle right here. So we have not, in fact, found the correct angle in context. This is pretty normal for, like I said, applied settings here, and it's just something you have to learn to put up with. Really, the correct approach here is to think about the numbers that you have and the context you have and find the angle based on this answer of 60 degrees. 60 degrees is a reference angle, and it corresponds with the angle the actual terminal side makes with the x-axis. It's also making a 60-degree angle. And so what's really going on here is we stuck our points into our function, but because our function got one ratio, when we divided two negative numbers, we got a positive ratio. The negative divided by negative is a positive. So as far as the function is concerned, what we gave it was the same as a point in the first quadrant. Now again, we looked at it already. We could have produced a function that could give answers in the third quadrant, but it would be difficult to produce a function that did that unless it only gave answers in the second and third quadrants. So we've decided first and fourth, because they're more central, we're going to have to adjust this. So in this case, for tangent, if we look at the picture and we think about the context, it's pretty clear what that angle should be, because the reference angle is 60 degrees. Our terminal side here makes a 60-degree angle with the negative x-axis, which is 180 degrees. So the correct answer is 240. That is 180 plus 60. And this is the sort of reasoning that I suggest is the best for dealing with the fact that the reference angle you get from your inverse trig function is not necessarily the same angle as what you really want. And as far as details on how that works for each of the different inverse functions, I'm reluctant to give them, although I will here at the end. It's memorizing the different combinations is worse than thinking about it in terms of reference angle, unit circle, and a little bit of logic and or addition of angles. So my general advice for using these in context are, first, if there is no context, if you're reading through a book or doing some math and all you see is something like inverse sine of square root of 3 over 2, don't worry about what quadrant that angle might be in. The actual function itself, given absent context, assume just the default domain and range. So you're going to give an answer between negative pi over 2 and pi over 2, which in this case, pi over 3 is the correct answer. So you just give it and don't worry about it and move on. If you're in the middle of a word problem or you've been given a point that's not in the first or fourth quadrants, what you want to do is use the information you have to figure out which quadrant it's in, and then based on the reference angle you get, use your logic to figure out what the actual angle is. That's my best recommendation, and it takes a little practice, but I think that you will get there. So just the same way we did here. 60 degrees, that's the reference angle. I know where the 60 degree is over here on the left, so I figure, 180 plus 60, I can see it. I mean, draw yourself a little picture is generally pretty helpful. If you are the crazy person who's just like, no, just give me rules to memorize, here they are. If you're using arcsine and you get an alpha, but it's not in the correct quadrant, you're going to want to use 180 minus the reference angle. Now, for cases where the angle you get is negative, this will still work because it'll actually give you 180 degrees plus that angle, which will give you the correct value. Because what you'll be looking at is you want an angle on the left, and you're going to give an angle on the right. So for negative angles, it'll give you in the third quadrant instead of the fourth quadrant, which is exactly what you need for sine. Arc cosine, you're getting angles between 0 and 180, or 0 and pi. Oh, sorry. And so the correct thing to do to adjust them are, if they're negative and well, if they're the wrong sign, if you have you got the angle and you wanted something negative, just change the sign. Although if you're looking for an answer between 180 and 360 degrees, what you actually do is subtract your alpha from 360. It'll give you the correct answer. And so if you're looking to memorize, this is what you're going to memorize. Arctangent is actually the easiest to remember. So if you're going to memorize one of these, and then just make sure that you can always use one of these, arctangent's the way to go. Because if your reference angle is not in the correct quadrant, the correct angle is always 180 degrees off sync. So you just keep adding 180 degrees or pi, if you're doing radians, until you get an angle that's in the correct position, 180. So, and really, opposite and adjacent I was a physics background, so the context I were using it was vectors, where generally what I had was an x and a y, and I'm trying to deal with the angle of the hypotenuse. So tangent was most useful. Anyway, just add 180, you're good to go. That's the end. Like I said, fewer examples, a little bit more talky. When you start getting into the examples, I think you're going to see how these work if you paid attention to the video. So like I said, you're going to have to use a little bit of logic, but I believe that you can do it. And also, if you're in my class, I'll be here to help. And if not, find yourself a good math teacher. Have a good day.